Hello everyone. My name is Youngwang Kim, professional consultant in Virtual Lab. Today I will talk about introduction to MatSQ Calphad and the method for using MatSQ Calphad. Here are today's contents. Firstly, I will introduce characteristics of MatSQ Calphad and talk about available database in MatSQ Calphad. Secondly, in MatSQ Calphad, there are 5 types of thermodynamic calculation service. So I will talk about how to use individual service. Let's look at the first topic, MatSQ Calphad. Calphad is originally calculation of phase diagrams, but was later expanded to refer to computer coupling of phase diagram and thermochemistry. Phase diagram is basically described by Gibbs free energy. Here is formula is Gibbs free energy for binary system. In this formula, particularly the L parameter, which is mixing energy, is important. By the L parameter in the phase diagram, liquidus line and solidus line are defined. Liquidus line and solidus line. Therefore, in the Calphad, it is important to well define Gibbs free energy parameter from appreciate experimental information. Normally, when manufacturing alloys, it is important to observe the microstructure. This is because the microstructure directly affects alloy properties. So if microstructure information are computational predict before fabricating alloys, the manufacturing process can be controlled more economically. Therefore, until now, the most useful prediction tool for the microstructure information has been the Calphad method. The present, many researchers use some Calphad softwares such as SumCalc, Panda, Backstage, Empty Data, or something like that. However, to use the Calphad software, tens of thousands of dollars should be paid. In addition, the cost of database should be paid separately from the cost of Calphad software. Therefore, our group developed MatSQ Calphad based on Open Calphad to make it easier to access while reducing cost. In our service, just $1 is paid to get one phase diagram or thermodynamic information. Generally, thermodynamic database for multi-component system is based on Gibbs free energy formulas for binary and ternary systems. Sometimes, to develop thermodynamic database for multi-component system, the Gibbs free energy formulas for related to quaternary system are needed. Our service provides two commercial databases such as steel and high entropy alloy system, and for free database. Our steel database is the origin version of TCFA series in SumCalc. This database was developed by Professor Lee, who is global analyst of thermodynamic field. The database has considerable accuracy within limited alloy composition range. Also, the database has been used by some researchers. Our high entropy alloy database was also developed by Professor Lee's group. This database is added vanadium to Cantor system. In this database, all of the binary and ternary systems were assessed, and some quaternary systems were assessed. Also, the database has been used by some researchers. If you want to get MatSQ Calphad information in more detail, you can see our website. If you click this one, our website provides information of MatSQ Calphad and database in more detail. From now on, I will talk about how to use MatSQ Calphad. MatSQ Calphad provides 5 types of thermodynamic calculation modules. Originally, the previous Calphad softwares provides amount of thermodynamic information. However, in fact, actual field of manufacturing and developing materials, in most cases, some thermodynamic information has been applied. So, among amount of thermodynamic information, our group screened the information necessarily required in the actual industry or laboratories. And then, in order to obtain this information more easily, our group finally developed 5 types of these modules here. Before starting tutorials, there is something you need to prepare. First, please open your web page and enter MatSQ.com. Materials scale is optimized for Google Chrome. Second, please sign into the MatSQ. This is MatSQ Calphad interface. Firstly, let's see the list equilibrium module. In the list equilibrium module, we can get thermodynamic information at given temperature, pressure, and composition. As shown in the following figure, we can get volume, mass, energy, Gibbs energy, enthalpy, entropy, and the phase information of a system at the given condition. This module is one of the useful modules when researching or developing materials. Let's start tutorial of this module. We will get thermodynamic information of steel. This page is MatSQ Calphad page. Please click this one. In this page, we should select alloy element. So please click this part. Then please select 6 types of atom. 6 types of atom. From manganese, iron, nickel, molybdenum, nitrogen. Yes. If you select atoms, please click this one. This one. And please select the following database. And click this one to select all pages. Next, please input the condition. Input the condition of the information you want to obtain, as shown the following figure. So, nickel is 0.05, manganese 0.1. This is weight fraction. And input temperature, given temperature, and you can change more fraction or weight fraction type. This calculation is a weight fraction type. If you input everything, please write job name and start the job. If you click start job, after a while, you can see the result like the following figure. Yes. I want to introduce 2 examples of applying this module. The first example is the study for inducing the multi-static transformation in high entropy alloys. In this literature, after initial heat treatment, the microstructure was observed as the FCC single phase regardless of nickel composition. However, after stringing was given at room temperature and lower temperature in alloy with lower nickel content, multi-stick transition occurred. In order to reveal the cause of this phenomenon Calphad was used. This calculation is to compare Gibbs free energy of BCC with Gibbs free energy of FCC, evaluate the possibility of the multi-state transition. Well, when using Calphad, it was confirmed that the more the nickel content was decreased, the higher the stability of BCC. So this literature explained that the strain energy can be the origin of inducing multi-state transition in the alloy that has high stability of BCC at lower temperature than room temperature. The second example is the high throughput calculation. The information obtained from this equilibrium module can be applied to materials big data. Actually, one team of accredited national laboratories performed the high throughput thermodynamic calculation based on the thermocalc software. In their study, data obtained from high throughput thermodynamic calculation was used as microstructural information. So these data have clarified the relation between microstructure and creep resistance. Also, these data have developed the machine learning model to predict creep resistance. In present, we are developing high throughput calculation module in MatSQ Calphad, and then we look forward to using the high throughput calculation in the near future. Yeah. Next, let's see the binary phase diagram module. The principle of binary phase diagram was already run in undergraduate period. The binary phase diagram is determined by Gibbs energy curve in individual phase. So the quality of thermodynamic database is determined by how well model parameters of Gibbs energy curve are optimized. In the binary phase diagram, normally there are 5 types of reaction. Since this content is included in the thermodynamic textbook during the undergraduate period, we won't go into more detail here. So let's start the tutorial of this module. We will get iron manganese binary phase diagram. Please click this. Please click this. Okay. In this page, we should select alloy elements. So please click this part. Then please select iron and mangan. Then please select the following database and click this one. Select all phase. Here is one thing to notice. If you want to calculate binary phase diagram of other systems, depending on the situation, you should select relevant phases of the target system in the select phase part. This is because in the case of selecting all phase, the calculation to minimize Gibbs energy curve can be performed complexly and accurately. Example of this situation can be found in open research of MatSQ on web page. In these cases, iron and mangan system, the condition of the information you want to obtain as shown in the following figure, and input start temperature, is 400 Celsius and final temperature is 2400 degrees Celsius, and types is weight fraction. So if you put everything, please write job name and start the job. You can get final result of iron mangan binary phase diagram. If you want to control axis range, y axis range, or axis range, please click right mouse button, yeah, and range value. Yeah. In this section, I want to explain polar equilibrium. The following left figure is for equilibrium iron carbon binary phase diagram. However, in practice, when manufacturing carbon steel in the microstructure, not graphite, but FECC cementite exists. Energetically, graphite is more stable than cementite. However, in aspects of thermodynamic velocity and reaction, practically, it is impossible for graphite to appear in the microstructure. So, if you want to get polar equilibrium iron carbon binary phase diagram to represent cementite, in the select phase part, you should suppress graphite. Finally, you can get the result like the following right figure. This example also in open research from MatSQ webpage. Depending on the situation, the select phase part can be usefully utilized in not only binary phase module, but also other service modules. Occasionally, the binary phase diagram can be utilized to estimate the segregation tendency of alloying elements. In the binary phase, if there are two-phase region, intermetallic compound, and spin-order decomposition, alloying elements may not mix well in solid phase of major elements. For example, in the iron manganese binary phase diagram, the range of manganese can be mixed in iron-rich BCC. Solid solution phase is narrow. In addition, in the iron mangan binary phase diagram, there are two-phase regions. So if the cooling is performed after annealing at the following point, the quantity of manganese in grain boundary can be larger than quantity of mangan in the BCC matrix phases. Yeah. Maybe this part is grain boundary content. Maybe this part is in BCC matrix. Actually, normally in manganese steel, the segregation of manganese in grain boundary is observed. So next, let's see the ternary phase diagram module. The ternary phase diagram consists of three types of the binary phase diagrams. The following left figure indicates four ternary phase diagrams. According to the viewpoint, the ternary phase diagram can be divided into three types, such as liquidus projection diagram, isothermal section diagram, and isopressor section diagram. Liquidus projection diagram is the diagram to track a liquidus line of ternary phase diagram. Unfortunately, our service cannot calculate liquidus projection phase diagram. Isothermal section means the phase diagram at a certain temperature of ternary phase diagram. In the MatSQ Calphad, ternary phase diagram module provides isothermal section types. Isopressor section means the vertical section of ternary phase diagram at the certain composition. Yeah, vertical section. So if you use user defined diagram module, you can get this phase diagram. The following figure indicates how to read the composition on isothermal section of ternary phase diagram, particularly in case of all ternary phase diagram, focusing A side and C side as a reference makes the composition on the isothermal section easier to recognize. Let's start the tutorial of this module. We will get isothermal section of Fe, nickel, chrome, ternary phase diagram 800 degrees Celsius. Please prepare MatSQ Calphad and please click ternary phase diagram module. We should select all elements. Please click this part. Then please select Fe, Ni, chrome, and then please select a filing database and click this one to select all phases. Next, please put the starting point as shown in the following figure. So nickel is 0.4, chrome is 0.3, and temperature is 800, and friction type is more friction type. So if you put everything, please write job name and start the job. After a while, you can get the result like the following figure. So when using a ternary phase diagram module, there is something to keep in mind. You should be careful when putting start point. If you put this value and this value and click start job, maybe you see this message because incorrectly enter a starting point for global minimization, you cannot obtain accurate ternary phase diagram. In addition, the error message can be present like this page. So I will explain this problem in more detail on the next page. So one point is the start point to get this phase diagram. The other point is the start point to represent error message. If starting point for the calculation of phase diagram is on timeline in two-phase region, maybe this region FCC and this region BCC, so this region FCC, yeah, so two-phase region. The phase diagram cannot be calculated since minimum values of Gibbs energy functions are not found. Therefore, this error message is presented. So one needs to keep this point in mind for using this module. Next, let's see the multi-component phase diagram module. This module is the most useful feature to solve material problems and to develop new materials. As shown in the following figure, the multi-component phase diagram provides the information on the phase types and the phase fraction according to temperature. Therefore, this module can be utilized to predict the microstructure, to design new alloys, and to set heat treatment conditions. Let's start the tutorial of this module. We will get a multi-component phase diagram of high entropy alloy. Please click the multi-component phase diagram module. We should select alloy element, so please click this part. Then please select 5 types of atom: vanadium, chrome, iron, cobalt, nickel. If you select atoms, please click this one. Then please select the following database and click this one to select all phases. Next, please put start point as shown in the following figure. So major element is iron, nickel is 0.15, chrome is 0.1, cobalt is 0.2, vanadium is 0.1, and start point temperature is 1200, and these two temperature are range temperature, and friction types, weight types, and define the job names and start job. Sorry, more friction type is correct, not weight types. You can get this result. Next, practically, the calculation result that you just obtained, like the following figure, was used to find the heat treatment condition. When the researchers manufactured the FCC single phase of high entropy alloy, due to this phase diagram, they could control the heat treatment condition like following condition. Let's practice this module one more time. We will get the multi-component phase diagram of medium manganese steels. Please prepare the multi-component phase diagram modules. This page, same. Please click this part and select 4 types of atoms: iron, manganese, silicon, and carbon. If you select the atoms, please click this one. Then please select the following database and click this one to select all phases. Next, please input the starting point as shown in the following figure. So major element is iron, manganese 0.07, silicon is 0.01, carbon is 0.0014, and temperature is a following value. Then friction type is, this case is weight friction type. Yeah. If you input everything, please write job name and start the job. After a moment, you can see the region like the following figure. One literature showed that multi-component phase diagram could be used to predict the initial microstructure in medium manganese steel. In this literature, the calculation value of phase fraction of initial retained austenite at 600 degrees Celsius was 42%. Also, the experimental value of the phase fraction of initial retained austenite was 42%, the same as calculation value. I confirmed that our calculation will reproduce the phase fraction of initial retained austenite for medium manganese steel. The last module, let's see the user-defined diagram module. This module is also the useful feature to solve materials problems and develop new materials. Our user-defined diagram module provides the two kinds of phase diagram. One is isothermal section, the other is isopressor section of multi-component phase diagram. So firstly, I want to explain the calculation of the isothermal section. As a part of the calculation of isothermal section, we will get the diagram to predict the solubility of vanadium carbide in austenite steel. Please prepare MatSQ Calphad. So please click User Defined Phase Diagram Module. You should select alloy element. So please click this part. Then please select 6 types of atoms: iron, chrome, vanadium, molybdenum, silicon, carbon. 6 types of atoms. If you select atoms, please click this one. Then select the following database and please click this one. Select only FCC. Select only FCC. Next, please put start point as showing the following figure. So molybdenum 0.1, chrome is 0.005, silicon is 0.001, vanadium is this one, and carbon is this one. Temperature, given temperature, this case is 1050 degrees Celsius, and friction type is weight percent type. This calculation like ternary phase diagram module, in order to obtain user-defined diagram more accurately, the starting point should be specified well because the phase diagram is determined by minimizing diffuse energy curve from the starting point. After putting starting point, please set axis as the following figure. Mean value is 0, and maximum is 0.015. Increment this value, and x-axis is vanadium contents. X-axis is vanadium contents, and y-axis is carbon contents. and min, maximum, increment, and you input like this value. Please write job name and click this one. So after Y, you can see the result like the following figure. If you use list equilibrium module, you can get the information on the areas in the following left graph. Right graph figure shows the result of checking the area. In the graph by using list equilibrium model. Typically, isothermal section diagram can be utilized to control carbide in steels. It is very important to control carbides because the formation of carbides affects intergranular corrosion. In practice, the formation of chrome carbide cause the chrome depletion in grain boundary. Here, intergranular corrosion in steels normally occur in the chrome depletion regions of grain boundary. Therefore, when manufacturing steels, it is important to control chrome carbide. The following figure was obtained using our user-defined phase diagram module and list equilibrium module. The following figure shows the change of phases according to the quantity of chrome and carbon. This figure makes it possible to control the amount of chrome and carbon according to desired microstructure. Therefore, the isothermal section diagram can be usefully utilized to predict the change of microstructure at a certain temperature according to the amount of types of alloy element. Yeah. The next, as a part of the calculation of isopressor section, yeah, we will get the pressure section of phase diagram of high entropy alloys. Please prepare user-defined diagram module of MatSQ Calphad. In user-defined module, please click this part and please select 6 types of atoms: vanadium, chrome, manganese, iron, cobalt, nickel, and please click this one. Then please select following database and click this one to select all phases. Next, please put starting point as the following values. Pressure section is x-axis composition and y-axis temperature. Tie content is manganese, so this value, and depending element. Chrome is depending element. So please set axis as following values. So x-axis is mangan content. So minimum 0, maximum 0.1, increment is this value. Y-axis is temperature. So start temperature and final temperature increment value. Please write job names and click this one. So after a while, you can see the result like the following figure. So if you use list equilibrium module, you can get the information on the areas in following left figure. The following right figure shows the result of checking the area in the graph by using least equilibrium module. Yeah. One literature showed that the initial microstructure of these alloys was FCC single phase, regardless the change of cobalt during annealing at 900 degrees Celsius. However, by the change of cobalt composition, trip behavior occurred during tensile deformation at the low temperature. Our calculation shows isopressor section of phase diagram of these alloys and gives free energy difference between FCC and ECC at room temperature according to the quantity of cobalt. The increase of stability of BCC can induce martistic transformation during tensile deformation. This point is also mentioned in the literature. Yeah. Therefore, the isopressor section diagram can be applied to predict microstructure and set heat treatment condition for unknown alloys. So far, I have explained the introduction to MatSQ Calphad and explained how to use our Calphad module. Thank you very much.